Okay, so I'm going to talk about waves, and I'm also going to try and illustrate how fun it is to be a scientist, especially one that likes to go out surfing and whose work is sort of involved in science. First off, I like to surf, and I used to ride a Carl White board, a Barracuda. There's a little right there. And my talk, I basically want to go over three things. Talk a little bit about myself, a little bit about my work, and then talk about waves. So first off about myself, my parents moved to Victoria like when I was grade 12. And I kind of want to do this so I can try and inspire the younger guys in the audience here to try and get into the science. That's the purpose of my talk. So moved to Victoria, I got some advice from a friend of my dad saying, just go to UVic, take some science courses, figure out what you're going to do, because I had no idea what I was going to do. And when I was doing that, I got into physics. I had this awesome first-year physics instructor, and away I went. Also, when I was doing that, I picked up surfing, and I wanted to have some money to buy a couple boards and pay my tuition. So I went into co-op education, which is basically every other term you go out and you work in your subject area. In my case, it was physics. So I started out in acoustics. I did some astronomy and some other cool stuff. So while I was doing that, whenever I could, I went out surfing. And around where we surf, it's cold out there. But as long as you're shredding, you stay warm. And one of my co-op terms, I ended up in Hawaii doing astronomy, and it was toasty warm, and I liked that. And I didn't have to wear a wetsuit. So after that, because of my experience in doing acoustics, I ended up doing ocean acoustics. And I started on my Ph.D. through one of my supervisors that I kind of work with. And I've been doing that ever since. And doing a Ph.D. is awesome. And doing grad school, masters, all that stuff is awesome, especially in science, because you get paid. And another benefit is that you have free time. Well, not free time. You have flexible hours to go surfing. So when the swell is really good between 6 a.m. and 10 a.m., I'll go out and surf, and then afterwards I'll come back to the office and work till 10 o'clock at night or whatnot. And that's great. I get to surf quite a bit. And also, being a scientist, after I finish, the same thing applies. I just get paid a bit more, and it's great. So onto my work. I make seabed maps. So the funky colors you see here are different types of seabeds. This is a map of an area near Sydney, BC, where we do all our testing and stuff. And I've developed a technique that allows me to take, your ordinary depth sounders and determine what the seabed is made out of. And that's hopefully an advance that people will use widely to do a lot of oceanography and stuff. So just quickly about the stuff we use, it's actually fairly simple. I use a little transducer that's off the side of a boat here. We drive around. We launch off of small boats. I use laptops, echo sounders, a bunch of equipment, a GPS, and a whole lot of duct tape. Duct tape's very important for my work. And we verify what the acoustics tells us with grab samples, which is a little bit of muddy work. And I've got some grab sample stuff in the back. I can show you kind of the stuff we pulled from the seabed. And the cool thing about my work is it is sort of involved with surfing in that we measure bathymetry, which is the topography of the seabed. And from that, you can try to predict what the surf is going to be like on the coast. So this is a map of seabed topography in the same area. It goes deep here and it goes up, and then you've got rough spots and all sorts of stuff where the waves kind of shoal around and things. So I'm just going to show you a little slide about some of the other scientists who are working in the science of surfing. And there's a couple who are directly involved. And my good friend Bryson here, he's got this cool picture up on his website. He's a sponsored surfer from Sitka. I don't know if you heard of Sitka. There's like the big local surf brand. Anyways, last year, he and his buddies sailed around the world raising awareness for plastics in the ocean. That's this ocean jibe thing. And now Bryson is working on his PhD using bathymetry from echo sounders such as mine to try to figure out what the surf is going to do. And he's done all sorts of cool things like put GPS on surfers, record what they're doing and all this stuff on the waves and stuff. So the other cool guy, this is our friend here, Walter Monk. He's the legendary surf scientist. He was the guy who first came out with the surf forecast back in 1945, the very first. And what was going on in 1945? World War II. So he did the surf forecast for the D-Day landings. It was the very surf forecast. And my friend Paul, who's a climate scientist who does a lot of surfing as well, he got him to sign a surfboard, and he was pretty stoked about that. He actually glassed over top so the signature wouldn't rub off or anything. He was so stoked. These guys here, this is Alex Hay, who's a professor at Dalhousie University. And if anybody wants to go into the science of surfing and that sort of thing, he's one of the guys you could go and study under. And these are all his grad students. Then they do oceanography and stuff like that, that involved in surfing a little bit. This is my friend Johannes. He's a professor at UVic who also does some wave stuff. He does more acoustic stuff, similar to me, but he actually does the acoustics of waves, which is pretty cool. And my friend Dougal, who could have done this talk today, he's just starting his master's. We go surfing out together lots. He's also doing acoustics of waves too, so it's pretty cool stuff. I just wanted to inspire you guys and say there are scientists out there working in surfing. Okay, so on to waves.
What are
Waves.
the acoustics of waves?
Well, when waves break, they make a crashing sound, right? So that's basically, you listen for that with, I got a hydrophone back there I can show you. You can also, what Johannes does is he uses a side scan sonar to look at the waves from underneath. You can actually track them as they propagate along the surface.
What is he studying in terms of acoustics? What's he all about?
Well, Johannes actually, I worked with him on this a little bit. The wave equation for waves, like the whole physics behind it, is a nonlinear equation. So the first part you can linearize. Waves go at so many kilometers per second across the ocean, and they have a constant speed. But the second term of the equation, the nonlinear part, says that small waves interact with big waves to make bigger waves, right? And that's what he was actually studying. So that's a good question, leads into this slide. And that's how waves are formed. Wind blows on the surface, little waves merge with bigger waves, and you get even bigger waves, which are called swells. Swells go much faster than small waves, and that's also part of the nonlinearity of ocean or wave physics. So fast swells, swells are fast, and they move across the ocean. I'll show you that in a second. But the thing is that from the wind and the length of the fetch, which is the size of the ocean that it blows over, the strength, the duration, we can predict wave height and period, which is very important too. So given that, you can propagate the swells across the ocean and figure out where they will hit and how strong they will be. So here's actually a model from NOAA. It's showing, it's not my favorite, but it's showing at least an animation of waves being formed, like right here, they're being formed, and then they're propagating across the coast, and in 140 hours, 45 hours, we're gonna have awesome surf. So that's next week sometime. And right now we're actually under pretty good surf conditions too. So, and down here I've got another little animation. This is how waves propagate in the ocean. They propagate as groups, in that the groups don't move very fast, but the swells move faster than the groups. And this is how we have sets of waves. We have sets between either 2 and 11 waves. So then you have a whole bunch of big waves, then there's no waves, then a whole bunch of big waves. And that's actually quite useful for surfing, because you're trying to get out there, you're getting pounded by the big waves, and then you get a break, and you go, oh, I can get out. And you paddle out. Then you can rest for a few minutes before the next set of waves comes in. That's pretty cool. Okay, so as the swells come towards shore, they undergo a process that's kind of complicated, but I can try and explain it to you really quickly here. So in the open ocean, I'll use my laser pointer. The water molecules in a wave move in a circle. I don't know if you ever felt this on a boat, but you kind of feel this kind of circular motion, right? And as the waves come closer to shore, the circle gets squished into an oval, and more until the oval gets so small that, and the wave stacks up, that eventually it breaks, right? So here's another little animation of how this works. So ocean swell comes in, long period, fast-moving waves. As the water bathymetry gets shallower, the waves stack up, slow down, and it gets steeper. And when they get steep enough, they eventually fall over and collapse into a breaking wave. There are different places on the coast where this process happens. Reef breaks, point breaks, and beach breaks are the different locations. Let me quickly go over those three. Here's a point break. This is my favorite point break ever. Carl will probably recognize it. You guys probably recognize it. This is a seabed survey of bathymetry we used with an echo sounder that my friend Bryson and I did. And we just tried to figure out what the bathymetry was there, where we were surfing, and how the bathymetry affected the surfing. And it's pretty cool, because I know that I usually line up here, and you drop in, you get barreled through here, you try to make it through the section, and then through this section here, you can do cutbacks and floaters and things. So it's pretty cool. So we basically surf along this yellow contour here. I thought, wow, that's really neat. I'm not going to tell you where this is, because it's a secret. Surfers have a bit of a we don't talk about where we surf actually, so can't tell you anything about that. So this is a simulation of waves coming on a reef break. I don't know if you can see it too well, but there's this circle here. That represents a shallower area on the seabed. So as the waves come in, they're parallel and they're straight. And as they hit this shallower area, they get squished up and they move together. It's called a process called shoaling or refraction. And they bunch up and they break right about here. And then you can surf this along here. It's pretty cool. And beach breaks occur on coasts like right here. Oh, where do you think this image is of? Oh, wait a minute. We're right here. This is North Chesterton's, and this is Cox Bay. I'll probably be here this afternoon. And these are both beach breaks. Basically, there's no real topography that makes the wave breaks. It's just a nice sloping sand. This is the best area for beginners to learn how to surf. So depending on the topography, we have different types of waves. The three main kinds are spilling, plunging, and surging. Spilling usually happens at beach breaks. There's a low sloping seabed. The waves kind of crumble from the top. It's easy and safe. Plunging waves have a moderate slope, and they produce barreling waves are for experts only. Surging waves, actually, if you look out the window right there, those surging waves are right there. Where basically, rocks and cliffs are surging waves. I'm just going to end my talk with a couple pictures of spilling and plunging waves. Basically, my two favorite spilling and plunging waves. Spilling waves, you can often longboard because it's not very steep. Plunging waves, you want shortboard so you can make that section and tuck into that barrel. So